Partial differentiation, introductory situation 1. Consider a rectangular prism or cuboid with a square base. We can see that this rectangular prism has a base which is x by x and a height of y. So v is equal to x squared times y. So v is a function of x and y if x and y are allowed to vary independently. Consider increasing x, thereby increasing the volume by increasing the area of the base while keeping y constant. So that would look something like this. The increase in volume is all due to the increase in x, i.e., we're looking at dv dx, keeping y a constant. We denote this by this notation. Note how the d's are written here. You'll hear various pronunciations of this if you look online, but I always just call it dv dx, but it's the curly d. When we perform this partial differentiation, we treat y as a constant. So, in other words, in v equals x squared y, the y is treated like it's just a 2 or a 3. Therefore, dv dx is equal to 2xy. Think about if y was 2 and this was 2x squared, it would now be 4x. If y was 2, this would now be 4x. So the y has played no active part in the differentiation. It's just been treated as a constant. Now consider increasing y, thereby increasing the volume by increasing the height while keeping x constant. So that would look like this. The increase in volume is all due to the increase in y, i.e., we're doing dv dy and keeping x constant. We denote this by dv dy with the curly d. When we perform this partial differentiation, we treat x as a constant. dv dy is therefore equal to x squared. If the x squared was a constant, say 4, then v would be 4y, and we know that dv dy would be just 4. So if it being x squared y, x squared is treated as a constant. It's just x squared.